Hello, thanks for joining me. Today we're looking at pulleys on inclines. What we're going to do here is we're going to figure out the acceleration of this system and we're going to figure out the tension in the string. So, hey, let's start with the free body diagram. Where else would we start? I'm going to make a dot that's going to represent my 10 kilogram object and a dot that represents my 6 kilogram object. 6 kilogram object is easy. We got the force of gravity, which is m times g, which is 6 times 9.8. 58.8 newtons. And the only thing touching it is the string, so there's going to be a tension force, Ft. Okay, over to the cart. Also has a force of gravity. And that's going to be 10 times 9.8, which is 98 newtons. Now, where are the contact points? The wheels are contacting the incline, and the string is contacting the car. So where the wheels touch, we're going to have a normal force. There could be friction, but let's do this without friction. And of course, where the string touches, there's going to be a tension force. So without any friction, those are the only forces acting on this. Now, when this accelerates, it's going to accelerate either up or down. That's an interesting thing to think about, which way it's going to go. But nevertheless, we always want to have our axis parallel to the acceleration. So that's why I'm tilting the axis. Maybe even more importantly, in a pulley problem, the string itself represents your axis, which is going to curl around the pulley and come down this way. We do have to decide on a positive direction for our axis. It doesn't matter, but once you decide, you got to stick with it. So I'm going to say this way is positive. And I like to draw arrows throughout my axis to remind me of where the positive direction is. Okay, having done all that work, I think we can jump into the Newton's second law equations. No, we can't. Oh my goodness, I'm not following my own rules. Next thing we have to do is if there's a force at an angle, we need to find its x and y components. So starting at the tip of the force of gravity here, I'm going to drop my perpendicular down to the y-axis, and that shows me that the y component of gravity looks like that, and the x component of gravity looks like that. The angle of 30 degrees is going to be this angle in here. I'm not going to prove that in this video, but it's always true that the angle between the force of gravity and the axis that has normal force on it is the same as the angle between the incline and the ground. That's something to memorize. So what that does is it makes our y component adjacent. So I'm going to use cosine. Cosine of 30 is equal to adjacent over 98. And so if you do your math, adjacent equals 98 times the cosine of 30, and that's 84.87 newtons for the y component. If we do the x component, we're going to do sine. So the sine of 30 equals opposite over 98. Opposite equals 98 times the sine of 30, and that gives us 49 newtons. Okay. Now that I have all the components figured out, I can start putting things in my Newton's second law equations for the, really, I don't like to call it the x and the y direction in a pulley problem. I really like to call it the direction that's parallel. So that those little lines mean parallel. The direction that's parallel to the string. It's only ever forces that are parallel to the string that result in the acceleration of the string. With a compound body problem, the way to find acceleration is to combine the free body diagram of both objects together. Write down all of the forces on both objects that are parallel to the string. So let's start over here. This component of the force of gravity, which we figured out is 49, points in our positive direction. This way is our positive direction, and that's parallel to the string. So we got positive 49 there. And then we have this tension force, which is going to point the other way, negative. Going around the pulley, we encounter another tension force. This one is positive. And no surprise here, we should have a negative and a positive tension because they're going to cancel out because they're internal forces. And our last force we encounter is this full force of gravity here, no components. It's directly parallel to the string. And then we're going to divide by, since I added up the forces on all the objects, I have to divide by the combined mass, which is 10 plus 6. As I said, the tensions are going to cancel out. And so relatively simple algebra there, and we get an acceleration of negative 0.6125 meters per second squared. So let's just think a moment what that negative means. It means our acceleration is in what we are calling the negative direction, which surprisingly is up the incline. The negative direction is up the incline. I say surprisingly because this is a more massive object. This is 10 kilograms. This is only 6 kilograms. So an important lesson here, it's not the absolute weight of the object that determines which one is heavier. This one's obviously heavier, but it doesn't accelerate this way. What matters is how much force is pulling parallel to the string. Here we have 58.8 newtons pulling in this direction. But over here, we only have 49 newtons pulling in that direction. It's a tug of war between the 49 and the 58.8. And obviously, the 58.8 is going to win. All right, let's finish this up by finding the tension in the string. So to do that, astute solvers of compound body problems will know we got to focus on just one object, not both together. I always like to do the one that has the simpler free body diagram, and I would say it's this hanging mass right here. So in that case, I'm going to do the acceleration is equal to the positive force of tension, negative 58.8. And since we're only doing that mass, I'm going to divide by only its mass, which is 6. And of course, we can fill in for the acceleration over here, negative 0.6125. So that's a pretty simple equation to solve for. And you know what? I didn't solve for it. So you can do that on your own. Okay, I paused it for a second while I calculated that. And what I got was 55.125 newtons. All right, hope this video was helpful.